Hello friends, welcome to the next part of this design of a continuous floor beam. In this continuous floor beam, we have studied up to the design for flexure. Now in this part, we are going to study the design of a shear, that is design of the shear reinforcement. So that is the next step here. In that design of the shear reinforcement, as here we are dealing with that MDM, that is the moment distribution method, this loading calculation needs to be done again. Hence, the loading calculation is considered. Which load is to be taken? So, for span BC, if you remember that load calculation, there we had two terms, that WEQ SDL and WEQ BDL. There itself it was mentioned that B is for bending and S is for shear. So, now the terms related to S are to be taken here for the load transfer from slab to beam. Hence, this dead load is calculated, that WEQ DL from S4. As for span AB, it is the shortest span for S1. So there won't be any load transfer because of S1. So only load transferred from S4. Hence WEQ DL S4. It is S for one-way slab S and B. Both have same equations. That is why here any particular notation is not given. So that WEQ S DL S4 plus wall load plus self weight. All these things we already have calculated in that load calculation step. So from there itself these values are taken and this final value is obtained, and then it is multiplied with 1.5, that is the partial safety factor, to get its ultimate load as we are dealing with LSM. Similarly, for live load, that same calculation is done, that WEQS LL from S4. This value is taken and it is multiplied with 1.5 to get that ultimate value. Next to this, we need to go for the next span BC. So that next span BC, now in this span, here you can see that how exactly this calculation is done. So for this span BC, now we have that WEQ SDL from S2 and that SDL from S4. Because this span BC, it is associated with the two slabs S2 and S4. So from both of the slabs, that load due to shear will get transferred on this beam. So this calculation is done, taken, and then this wall load and self weight. So likewise this value is obtained, it is multiplied with that load factor, and then the ultimate value is obtained. Similarly for live load. And the same calculations are done for this span CD, and accordingly the ultimate values are obtained. Then the maximum loading is calculated for all the three spans, that is 1.5 into dead load plus live load. So here we have got these maximum values. For these maximum values, that MDM is carried out. So to carry out that MDM, here first of all those fixed moments are calculated. The method is same as that of the design for flexure, that WL square by 2, as there is not any another point load. If some secondary beam is acting, then here means wherever the secondary beam is acting, at that point its reaction needs to be considered, and accordingly these equations will change. As here any of the shear reaction is not there, only UDL is there, and for that UDL simply WL square by 2 will be taken, and accordingly these values are obtained. For these values, then find out the distribution factor. Now as this I is remaining same and the distribution factor, it is not depending on load, that is why here that distribution factor will remain same as what it is calculated for the design for flexure. Then by taking those distribution factors, here the moment distribution method is applied, and accordingly the support moment is obtained. In the same manner that method is applied, and in the same manner that moment is obtained. So here for support B, now we are getting that moment as 47.3, and support C, that moment is obtained as 82.13. that maximum value is taken. For this moment, then find out the reactions. Now see here, in case of the flexure design, by taking this moment we applied the redistribution, this moment was reduced, and then the section was designed. So as here there is a benefit of the reduction of the moment, and accordingly the steel needs to be provided. In case of flexure we reduce this moment, but as now here we are dealing with the shear, no need to reduce this moment, directly it will be considered for the further design or the further calculations. Hence we have shifted to the determination of the final reactions. Again that same method, the reaction due to fixed end moment, then the reaction due to external loading, and hence the final reactions. Based on these final reactions, now here you will get that shear force diagram for all the 3 spans. For the reference, here I just have taken that calculation for the maximum span. Rest of the two spans you can carry out that calculation by your own by referring to this. So for this maximum span, at its one end the reaction is 121.14 and the another end is 133.28. So for this shear force diagram, now we need to consider this left portion separately and this right portion separately. Means for this design calculation, these two portions will be treated separately as these two are having the separate reaction. So first we are considering this left portion. So for this left portion, this reaction is nothing but Vu max itself, so it is taken as that Vu max. Then next to the Vu max, we calculate that VUD, that is the ultimate design shear at the critical section, hence this VUD is calculated. Next to that, we calculate that maximum allowable ultimate shear, that is VUC max. This tau UC max, it is based on table number 20. This VUC max is calculated, and we need to check that this VUC max should always be greater than VUD, then only the section is treated as safe, or else you need to revise the depth of the section. So here our check is getting the section is safe, so we can proceed further. And the next calculation is for VUC, that is the ultimate shear resisted by the reinforced concrete. So this VUC, that is tau UC into B into D. So for this tau UC into B into D, this tau UC is based on the percentage of the steel. Which percentage of the steel is to be taken? The steel which is provided at support B only, this at support B, the provided steel at the tension phase, PT, percentage of the steel at the tension phase, that needs to be considered. So at that tension phase, we have provided 2 bars of a 10 mm through, those are the anchor bars, and 2 bars of 20 mm diameter are curtailed at that tension phase. So for these 4 bars, that AST provided needs to be taken, that is 785.40, and for this value now calculate its percentage. So here we are getting that percentage 0.84. For this percentage, find out that tau UC from table number 19. By interpolation you can get this value. So here that value is obtained, and then VUC is calculated. So this VUC is obtained as 54.53. Next to this VUC, you need to go for that ultimate shear resisted by the minimum vertical stirrups. Here we will be providing only vertical stirrups, hence only for that purpose the calculation is done, that is VUSV minimum. It is 0.4 B into D. This B is to be taken as 230 only, not BF, it will be taken as BW, because at support we are calculating the things, and at support it is provided with the rectangular section only, hence BW only will be considered. And for this span BC, the depth we have provided as 406, hence this 406 mm is taken, and accordingly this calculation is done. Next to this, there is the ultimate shear resistance of the reinforced concrete with the minimum stirrups, that is VUC plus VUSV minimum. So this VUC, here we have obtained that value 54.53. Okay, by mistake I have taken 51, it is 54 plus this VUSV minimum 37, and whatever this value you are getting, VUR minimum, it will be 94 point something, that is it should be less than VUD. Your VUD is 98. So if this value is less than VUD, then provide the design shear reinforcement. How to provide that design shear reinforcement? So this next step is there, that design shear reinforcement means this ultimate shear to be resisted by the shear reinforcement, that is VUS, needs to be calculated. It is equal to VUD minus VUC. So VUD was 98.28 and this VUC we are getting 54.53. So this is that VUS. For this VUS, now the spacing will be calculated and the zoning is to be considered. So the next step is that zoning of the shear reinforcement. In this zoning, the first zone, that is the design shear reinforcement. As here we need to provide this design shear reinforcement, this zone 1 is present. So here let us provide that hash 8 bars of 2-legged stirrups. What are those 2-legged stirrups? So generally in a beam, suppose this is that rectangular section of the beam, then in this beam we provide this kind of the stirrup. So for this stirrup, this is leg 1 and this is leg 2, hence it is treated as 2-legged stirrup. If this is increasing, then accordingly we need to check it that how it is exactly those legs are provided, means either 3 leg or 4 leg. Generally in case of beams it will be 2 legged only, so that 2 leg stirrups will be provided. Then that ASV is calculated based on this 8 mm diameter and 2 leg stirrups. As per the IS recommendation, even we can provide that 6 mm diameter also, that means minimum size of the diameter of the stirrup should be 6 mm, but as nowadays in actual practice it is provided with 8 mm. Here the calculations are done with 8 mm. Then next to this we need to find out the spacing of that shear reinforcement, that is denoted as SV. Now there is some change in the formula, that 0.87 Fy into ASV into D upon VUS, that is given in the clause number 40.3. From there you can refer. This VUS means that design shear to be resisted by the stirrups. So all these values are put, and here we have got its answer 336. Now for this spacing, again that criteria is given in IS code, that the spacing shall not be greater than 0.75 D or 300 mm, whichever is lesser. Hence these two values are calculated, that 0.75 D is 406 and it becomes 304 or 300 mm. So lesser value is 300 mm. Hence the spacing will be provided as 300 mm only, and hence it is written that provided #8 at 2-legged stirrups at 300 mm center to center. And for these stirrups, now the length of the zone 1 is to be calculated, that is LS1. It is equal to VU max minus VUR minimum upon WU. And for this length, means here we are getting that length as 0.66 meter from B. So from support B, that length will be provided. Then zone 2, that is the zone of minimum shear reinforcement. So this minimum shear reinforcement, just calculated spacing. Again for this spacing, that criteria is same, that it should not be more than 0.75 D or 300 mm. So in this case it is more than this value, hence provide the lesser spacing, that is 300 mm. So in zone 1 and zone 2, the spacing of the stirrups is remaining same, and the length of zone 2, here this VUR minimum will be used because VUR minimum is greater than VUD. So VUR minimum minus 0.5 VUC upon WU. It will give you that distance of the zone 2. After zone 1, this zone 2 needs to be provided. Then zone 3, that is the nominal shear reinforcement. So this nominal shear reinforcement is always provided at this nominal spacing of 300 mm. Hence it is directly written 300 mm, and the zone length is calculated 0.5 VUC upon WU. Here you will get this zone length. This was only the left part of that span BC. Similarly, we need to consider the right part of that span BC, because the shear force acting at right and at left is different. And now let us consider that right part. We will go in short. So that VU max for right part was 133.28. Then just calculate VUD. All the steps are same, only the values are changing little bit. Then VUC max, it will remain same. Just check that VUC max is greater than VUD. The section is safe. Then calculate its VUC. Now to calculate VUC, the steel provided at support C needs to be considered in the tension phase. So if you check the design of the support C, then there we have written that 2 bars of the 10 mm as the anchor bars, and 2 bars of 20 mm plus 1 bar of a 10 mm will be curtailed. Hence these total bars are considered here. So these are 3 bars of 10 mm and 2 bars of 20 mm. So the provided steel is this much, and for this provided steel calculate the percentage. So this percentage is calculated. For this percentage now calculate tau UC. So for this tau UC, then calculate its VUC. Then next to that VUSV minimum, it is 0.4 B into D, so again it will remain same. Then VUR minimum, that is that shear resisted by concrete plus vertical stirrups. So this value 95. If it is less than VUD, then we need to go for the design shear reinforcement. If it is greater than VUD, then go for the minimum shear reinforcement. So our VUD in case of right portion was 110, and we are getting that VUR minimum as 95, which is less than VUD. Hence go for the design shear reinforcement. So for that calculate this VUS, design shear to be resisted by the stirrups, that is VUD minus VUC, this 52.2. Then calculate the zoning. So the first zone, that is the zone of the design shear reinforcement. So calculate its spacing. Now here we are getting that spacing as 282. It is less than 3D or 300 mm. Hence provide #8 2 leg stirrups at 280 mm center to center. Then zone 2, that is the minimum shear reinforcement. First, before that, for this zone 1 we need to calculate its length, so that Vu max minus Vur minimum upon Wu. So here we are getting that value from support C now, because we are considering the right portion. Then go for this zone 2, that is the minimum shear reinforcement zone. In this zone 2, the spacing we already have calculated in the first part, that is for the left part. So that same spacing will be here, as that spacing is not less than 75D or 300 mm, hence directly 300 mm spacing needs to be provided. Hence provide that #8 2 leg stirrups at 300 mm center to center, and then calculate the dimension for that zone or the distance for that zone. So here that distance is obtained. Then go to zone 3. Zone 3 is the zone for the nominal shear reinforcement, hence the nominal spacing, that is 300 mm, that is the maximum spacing will be provided, and its length is calculated here as that 0.65 meter. Here this calculation is done only for that span BC, that is the maximum span. Based on that you can calculate it for rest of the two spans also. In fact, it is mandatory to calculate for the rest of the two spans, because then it may happen that there is not any need for the provision of the design shear reinforcement, and accordingly you can provide the lesser shear reinforcement, and hence based on the similar lines for the rest of the two spans also that shear reinforcement is to be calculated. And after calculating all these things, there is the next step, that is that reinforcement detailing. Means whatever we have designed, now it is to be shown in the diagram. So here the diagram is drawn. For span AB we had first of all this continuous beam is drawn, all the depths are shown. For span AB this depth was 233, for span BC the depth is 450, and for span CD the depth is 300, and these are the provided columns. Then first of all we have designed that flexural reinforcement or the main reinforcement. So for span AB it was 2 bars of 10 mm diameters as the main reinforcement, and 2 bars of 10 mm diameter as the anchor bars. So this thing is shown. Then similarly in span BC we have provided that main reinforcement as 2 bars of 20 mm diameter through and 1 bar of a 16 diameter curtain. So that same thing is shown here, 2 bars of 20 mm diameter through bars and 1 bar of a 16 mm diameter is curtailed. Then for span CD again that same calculation is shown. Now here you can observe that the bar from span AB is extended up to the opposite face of support B. Similarly here it is extended. So this detailing is done as per the ductile detailing, that is IS 13920. This much distance is to be extended, that development length is there, it should be extended into the next support, so accordingly it is extended, and here that hook will be provided with LD plus 10 phi, again based on that IS 13920, that is the ductile detailing of the reinforcement. Then at support B and at support C we have provided some extra steel. Now here you can observe that why that calculation was 2 bars of 10 mm plus the additional steel, because these 2 bars of 10 mm diameter, that is the anchor bars, so these bars will run throughout the span, hence at each and every support those bars are already provided. In addition to those bars we need to provide the extra top steel, hence that extra top steel is calculated. So at that support B we have provided 2 bars of a 20 mm diameter as the extra top steel. From support B that distance we have calculated for the actual point of cutoff as 570 mm, and towards means in span AB that distance, this is not the actual distance, and there was something 900 and something distance is there, so that distance is to be provided along this side. Similarly for span CD, in addition with the 2 bars of 10 mm we have provided extra 3 bars. Those 3 bars are 2 bars of 20 mm plus 1 bar of a 10 mm. So these extra top steel bars at support, and again their distances means at support B we have calculated their curtailment distance. So into span CD it is provided with the distance of 1406, and into span BC it is provided with the distance of 976. Next to that we have provided the shear reinforcement. Now the shear reinforcement is calculated only for the span BC, so that thing is shown over here. You can calculate it for span AB and for span CD, and then you can show it accordingly. So in the left span, that thing means first zone was the zone of the design shear reinforcement, then second is the zone of the minimum shear reinforcement, and third one is the zone of the nominal shear reinforcement. So here these zones are to be shown. The first zone, that is that zone of design shear reinforcement, here LS1 is to be shown, then LS2 zone of nominal shear reinforcement, and then LS3, that is the zone of this one is minimum and this one is nominal. Similarly, from this support also it will be considered that design, then minimum, and then nominal. These zones are to be mentioned. Now in these zones, here purposefully these different colors are used so that you can get the difference easily. The first zone is that design shear reinforcement. For span BC, towards its left side we have designed it that #8 two-legged stirrups at 300 mm center to center, and towards right it is designed with 280 mm center to center. So that detailing is shown. Then next to that LS1 there is LS2. So that LS2 on both sides, means towards left and towards right, it is provided with the distance of 300 mm, that is #2 at 300 center to center, and the in between that there is the zone of nominal shear reinforcement, and it is provided with the spacing of 300 mm center to center. So accordingly this detailing is done. In addition to this detailing, here you should mention that distances LS1, LS2, LS3, all these distances are to be mentioned. So here it is LS1, similarly here also it will be LS1, okay, then LS2, and then LS3. Here LS3 and LS2, these distances will be mentioned. After plotting all these distances, this is that elevation of the beam. Now in this elevation we need to draw some sections. Why these sections are to be drawn? Because at different points different reinforcement is provided in the beam. So to get that detail, basically to get the detail of the design shear reinforcement, those sections are to be drawn. So the first section A is taken, that is at support B. Now at support B we have designed this rectangular cross section, hence this rectangular cross section is shown. Now at support B, the tension reinforcement, that is only 2 bars of a 20 mm diameter. So at bottom these are the only 2 bars of 20 mm diameter through bars. Then at top, the very first thing is these 2 bars of 10 mm diameter, those are the anchor bars. So these 2 anchor bars are shown, and in addition to that this 2 bars of 20 mm diameter at the extra top. So here these 2 bars of 20 mm diameter as the extra top, here 2 bars will be shown. This one is 1 and second, so 2 bars of 20 mm diameter at that support, that will act as the extra top steel. Then show all the dimensions, that the total depth provided is 450 mm, width is 230, effective depth is 406, and these stirrups at this support B, so these are #8 two-legged stirrups at 300 mm center to center. So that detailing is shown, that is the section A. Then this another section is drawn, that is section C. Now this section C is at the mid span where we have designed the flexural section, means that T section is defined. So that T section is drawn, in between the depth is 450 and width is 230. Okay, then after that show this main reinforcement provided at the bottom. Now at this section C, all the bars are visible, that is 2 through bars and 1 curtail bar. So all the 3 bars are shown, that naming is done, 2 bars of 20 mm diameter through plus 1 bar of a 10 mm diameter curtailed. And at top of this section C, there are only anchor bars, so only these 2 anchor bars, 2 #10 anchor bars will be shown. This extra top steel will not be visible at this section. And these stirrups, so now this section is taken in the zone of the minimum shear reinforcement, that is LS2. So those stirrups are provided #8 two-legged at 300 center to center. So accordingly that is shown, and this much will be that BF, that is the width of the flange. This BF is done, this is width of the flange. Similarly, you can draw the section at this point D and at this point P. at this D, that is the section in the zone of nominal shear reinforcement, means these stirrups will be of the nominal shear reinforcement. And at this support C, means near to the C, we have taken that another section B, because even though this is the zone of the design shear reinforcement, but the spacing is different than that of support B. At support B, the spacing was 300 mm. At support C, the spacing is becoming 280 mm. Hence, two different sections are to be drawn. Again, at this point B, there will be the rectangular section, but at point D, there will be the flange section, that is this T-beam. Accordingly, additional two sections are to be shown, and then mention here the dimensions for these spans, that is AB 2230, then this BC 5730, then this CD. Okay, so all these dimensions are to be shown, and this is that complete reinforcement detailing for the designed section. Whatever we design, that design is kept with us, and at site only these reinforcement detailings are sent. If we are committing some mistake in the reinforcement detailing, then the reinforcement provided at site will be wrong. It will lead to the failure of the structure, or it will hamper the designed structure. That is why utmost care should be taken while we are mentioning or while we are providing these reinforcement detailing. So here we are ending with the design of the continuous floor beam. In up to the previous parts, it was the design for flexure. In this part, we saw the design for shear and then the reinforcement detailing. Thank you.